Okay. Today we'll start with the purification of water. What is the meaning of purification? Why we have to purify the water is to achieve drinking water standards. There are some standards given by the Indian Standard, that is Bureau of Indian Standard BIS. They will say that this much of these are the standards that the water should contain. Say for example some chemicals, pH or the hardness, metals, and there are some minerals. They should be of this much quantity. They will mention for a healthy human being. That's why we have to maintain that one. For that one, before distribution, and also we have to take care of the future contamination if any. For this purpose, we will be doing the purification of water. Then the available water must be, these 3 points we have to take care. The first one is good appearance. Water should be good in appearance and it should be attractive to the human human's taste, tongue. It should be attractive. These 2 points we have to consider, and we have to design a treatment plant. And in this treatment plant we are concentrating on screening. Screening means big particles will be removed. Big particles like stones, leaves, trees, bushes, or any dead animals. These all materials will be removed by screening. And after that there are some that look at here. This is a screen. Screen means this is a bigger in dimension. Here in bigger dimensions, the bigger particle will be arrested. The bigger particle will be arrested, and the water will be passing through the screen. But smaller particles, smaller than the these particles, they will be passing through the screen. Those particles can be removed in the sedimentation tank. These particles means we are targeting on such particles like clay or silt, or sand particles. These small particles are targeted in the sedimentation tank. Here in sedimentation tank, we will go through that one clearly. But there are some particles which will not be settled in the sedimentation tank. Say for example, colloidal particles. Colloidal particles will not settle in the sedimentation tank. For example, I will give you take a glass of water. In this glass of water, you put one drop of ink. When you put a one drop of ink, then this ink will be that dissolved in the water, or otherwise you put a one drop of milk. Then what happens? This milk particle is considered as a colloidal particle, but these colloidal particle will not be settled in the sedimentation tank. Therefore, we have to use some chemicals. Therefore, it is called as a coagulation tank. But after coagulation also there are some bacteria, and there are some color or taste will be there. Those are not removed in the screening and sedimentation. Screening, plain sedimentation, and coagulation, those are concentrated in the filtration. In this filtration we are removing some bacterial load we are removing, and we are some extent we are removing some color and taste also, odor also. Okay, these things are concentrated here. Disinfection, here there are some bacteria which might be left in the water. Those will be killed here in the disinfection. And in disinfection we are taking care of the future contamination. Means in future also, after 1 month or 15 days of water treatment, then also there should not be any increase in the bacteria load. Therefore we are taking care of that one in the disinfection. Then after that, aeration. If any dissolved oxygen is that what less in the water, then we will be doing aeration and increase the dissolved oxygen. Along with that, we will be removing the taste and odor in some extent in this aeration. And after that, we will be concentrating on hardness. Okay, if the water is too hard, that hardness can be removed in this process, that is a softening. Then after that we have a miscellaneous treatment. In this miscellaneous treatment we may add some minerals, or excess mineral can be removed. These two processes will happen in the miscellaneous treatment. For example, fluoridation, recarbonation, desalination, like that we will be having many miscellaneous treatment. Understood? But for any water supply scheme, we will not be providing all of them. It is all depending on the raw water. Which type of raw water you are having from the source. Based on that, you will be providing these treatments. Okay, now we'll go one by one today. The first one is screening. Here, as I said, that the bigger particles like trees, branches, sticks, and vegetation, fish, animal life or dead bodies, these bigger particles can be removed in this screening. Then provided in front of the pump. These screenings are provided in front of the pump. You know, most of the time in water treatment plant, we are not designing screening. Why? Because if you have this pump, if you have this pump, then pump will have a pipe here, and this pipe will have a screening here that usually we will call it as a footwall. No, we will call it as a footwall, and this will be provided. Therefore, most of the times we will not be having this screening technique in the water supply, but in wastewater supply we will be having this screening. But still, we will study that we have a coarse screens and fine screens. Coarse screens means the openings are bigger in size. Say for example, 2.5 to 5 centimeter opening will be there, and these coarse screens are vertical. You might be seeing this one. If there is a gutter here, if there is a gutter or any channel is there, then there will be one screening will be given. Most of the times in your bathroom also, that where that water outlet will be there, no, this water outlet will have this type of screening. Even if this is a wall, if this is a wall, and here you will provide a screening, vertical screening, which are of bigger in size, bigger in openings, that is 2.5 to 5 centimeter opening will be there. Usually these screenings will be made inclined, so that inclined with some angle theta, so that you can have some other benefits like to increase the opening area. This opening area will be increased. Why? Because here this is a vertical screen uh, for this much of depth of water. Then the same screen, if I make it in an inclined, then see the opening area is more here compared to this one. Because of that, we will be making some inclination. Then the reduces the flow velocity, because the area is increased here, flow velocity will be reduced, and makes the effective. Here removal also, it will be very effective. You can remove it if it is inclined, you can remove it very easily. Then here we will be measuring in the coarse screens, we will be measuring velocity not greater than 0.8 to 1 meter per second. This you have to by heart it. Many times they will ask in the competitive exams, like coarse screens, where velocity will not be more than the 0.8 to 1 meter per second. Weights removed may be manually or mechanically. If the screens are like this, then you will have some arrangement, some that puller. Then using this one, you can manually pull, or otherwise you can make some mechanical arrangement. Right? This is all about your coarse screens. If you come to the fine screens will be with the woven, means they will be of threads. Threads are woven like this, and there will be square meshes here. These meshes dimensions are not greater than 6 mm, means very small openings will be there, and this will be used in the fine screens. But the demerit of this one is frequent cleaning is required, otherwise chalking will be, that problem will be there in the fine screens. Understood? This is all about screening. And next treatment is a plain sedimentation. Now look at here in the screening, we have arrested the bigger particles, the particles of bigger size, like particles of greater than 5 mm or 2.5 5 centimeter or 2.5 centimeter. Those are arrested. But the smaller particles like sand, silt, these particles will be passing through the screens, that we will not remove it by filtering. Therefore, we have a plain sedimentation tank. Okay, the principle of this plain sedimentation tank is very simple, that you have a water tank here, you have a water tank here. Then if this is a water here, then if you put some dirty water here, dirty water will have some particles. No, dirty water will have some particles. These particles are very smaller in size. As I said, these particles are sand or silt or clay particles. Initially these particles will be floating in the water. These particles are floating in the water, but these particles specific gravity, these particles specific gravity is greater than 1, greater than water. The specific gravity is greater than 1 means after some time, after some time t, then these particles will automatically come and down, come and settle down. These particles will come and settle down. This is the advantage, means sedimentation tank will remove all the particles which has specific gravity more than the water, usually more than 1.2 we will consider. right? In what particles, which particles will be removed in the sedimentation tank? The question. The answer is the particles having specific gravity more than 1.2 will be removed in the sedimentation tank, irrespective of their sizes, right? Here it is said the most of the sedimentation will have that sediments will have a greater than 1, usually 1.2 also we can consider. They may remain in water because the turbulence, if the turbulence is retarded either by making the water stand still or move with a slow velocity. This one, what you do, here you will make a small slope, you will make a small slope here, so that this water will flow with a very slow velocity, very slow velocity. When this water is moving very slow velocity, in that time these particles will come and settle down, these particles will come and settle down. This is one advantage. Or otherwise you can make it like you can make the water to stand still for some hours. 3 hours the water will stand still, and after that you open this gate, then the water will go, clean water will go. Then again you allow the water to stand for 3 hours, then again you can remove it. Like that we can make some arrangements. Okay, they remain. If there is a turbulence, then what happens? Sediments will not settle down, that we have to remember. Okay, we have to stop the turbulence. Then also called, these are also called settling tank. These sedimentation tanks are sedimentation tank, sedimentation basin, or sedimentation clarifier, or clarifier they will call. These are the different names of sedimentation tank, right? We have two types of sedimentation tank. The first one is, sorry, this one, detention time. Detention time means how much time the one particle or a particular sample, water sample, will be remain in the tank is called as detention time. Say for example, this water entered here at a zero time, the water entered at a zero time, and this water will flow like this, and the sediments will come and settle this here, and this water will go outside. Then how much time it will take from here to here, this is called as a detention time. That is called as a detention time. Understood? Now we have got that detention time, that is the average time taken for this process, that is in hours we will be counting. Then types, we have two types of sedimentation tank, that is intermittent tank, and the second one is a continuous tank, right? The intermittent tank means that is a quiescent type. Quiescent type means shanta we will call, means silent, it will be standing still, the water will be allowed to stand still. Okay, the water brought to the rest, and then later allowed to move, later allowed to move. Then the continuous tank means will move with a very slow velocity, slow, so that both will be taking care, that is flow is also there and sedimentation is also there. These continuous tanks are designed as a rectangular type or square type. Rectangular, square, or circular in cross-sectional area. Top view, you can take a square area, that sedimentation tank, or rectangular sedimentation tank, or circular sedimentation tank. Usually, quiescent tank or otherwise intermittent tank we are not using nowadays. And give an example means the lake is the best example for intermittent or quiescent type of sedimentation tank. Okay, now theory behind the sedimentation tank, as I already explained you, the particles which have a more than the specific gravity of water, the particles having the specific gravity more than the water will settle down. For that one we have to stop turbulence, and we have to allow the water to flow with very slow velocity called laminar velocity, laminar flow. Then those particles will come and settle down. Okay, now then here in this one, settle down means what? Why the particles will settle down? This is a very important question in this sedimentation tank. See, this is a sedimentation tank, and the water is there here, the water will come from here, and after that water will go from here, right? This is your some opening is made here, the water will go here. Now why these particles will settle down? Because the first answer is they have a specific gravity more than 1.2 or 1, right? More than 1. Then the second one is they have some velocity, they have some settling velocity, they have some settling velocity, and water is also having some velocity. This velocity I will call it the flow velocity, and the particles will have its settling velocity. The particles will have settling velocity, and the water will have flow velocity. If your settling velocity is more, if the settling velocity is more than the flow velocity, then the particle will settle. If your velocity, this the flow velocity is more than the settling velocity, then the particles will escape. The particles will escape. They will not be removed. Therefore, here the condition is, first we have to determine what is the settling velocity of the particle, or otherwise you should know the information that which type of particles are entering, which type of particles are entering into the coagulation tank. This information you should know. Which type means what is the specific gravity of the particle and what is the diameter of the particle. Okay, these two information you should know. Then after that you allow the water, then they will have a specific settling velocity. Then you design the tank where the velocity, flow velocity is lesser than the specific this settling velocity, then the particle will automatically settle down. This is the principle. Therefore, first we have to worry about this one, settling velocity. The settling velocity, this is derived by Stokes, the scientist Stokes. He will derive this equation. The Stokes considered the principle of buoyancy. Principle of buoyancy is actual weight minus buoyancy. Then he will derive an equation. This equation you have to by heart. Okay, this equation initially by heart, but not exactly this one. I will give you later simplified equation also later. But this is the starting equation given by Stokes: 4 by 3 GD into G minus 1 by CD. Okay, this CD, what is this CD? Then that CD is called as drag coefficient. This is very very important. This drag coefficient depends on the type of flow. This CD depends on laminar flow, transitional flow and turbulent flow. We already have a definition. Laminar flow is a Re less than 1 for sedimentation tank. Transitional flow is Re 1 to 10 to the power of 4. Turbulent flow we have Re greater than 10 to the power of 4. This is the equation. As I already told you that if the flow is turbulent, then the velocity, that particles will not settle down. Therefore, we don't want this one. If the flow is transitional, then also we are not concentrating on this one. Therefore, we will not take this one. Then in the sedimentation tank, we will concentrate on CD equal to 24 by Re. By heart this one. This is very important. What is this Re? Re is a Reynolds number. Then the Reynolds number can be calculated by using this equation. And this Reynolds number we will substitute in this one and we will calculate, redefine the CD value. Then that redefined CD value we will substitute in this equation. We will get this. This is ultimate equation. This is ultimate equation for sedimentation. Right? And this sedimentation, here you concentrate what parameters we have here. The parameter is gravity constant 18 constant, but this is the particle size. Sorry, particle specific gravity. This is the particle specific gravity, and this is a d. D is the diameter of the particle, and neta is the viscosity of the water. Viscosity of the water in turn depending on the temperature of the water. It is depending on the temperature of the water. Therefore, we have an equation for 3t plus 70 divided by 100, that converted, mu is converted into temperature. We have one empirical equation here. If you are, be careful, if you are using this equation, then you should remember or by heart the units. That is the D you have to substitute in mm. D you have to substitute in mm, and you will get the answer in mm per second, and temperature you have to put it in the degree centigrade. Then only this will be working. Understood? Here one very important things are there here. This you have to remember. The things to remember is we have a three specific equations here for settling velocity. Of course, this is a general equation. This is a general equation. Here they have not mentioned anything, which diameter, which specific gravity, which temperature. They have not at all mentioned here. This you can use it anywhere you want. Right? But simplified equations also there. That is, this is the first equation, the second equation, and the third equation. Here, these three equations are specifically used when by seeing the diameter. If the diameter is less than 0.1 mm, I will draw one here chart. Let us consider one scale is a 0.1 mm, and the another scale is here 1 mm, and another scale is here greater than 1 mm. Now look at here, I have a scale here. The particles less than 1 mm is this one. The particles in between 0.1 mm and 1 mm here, and the particle size more than 1 mm is here. Okay, this type of particles we will use this equation. This type of particles will use this equation. This type of particles we will use This equation, that's it. You can by heart that. And the above all equations for spherical diameter, very important. We here the the scientist Stoke assumed that the particles are spherical in shape. Particles are spherical in shape. Then the question arises here: if particles are not spherical, then what happens? If the particles are non-spherical, then what happens? The Vs will be less if the if particles are non-spherical. For that, we have to multiply some uh, coefficients or some constants. Then we have to get it. Right? Next, factors affecting Vs. You can go through the equation. In the equation also, you will come to know the flow velocity is inversely proportional and the viscosity is inversely proportional. Size, shape is directly proportional and specific gravity is directly proportional. By seeing the equation, you can go through the factors affecting settling velocity. As I said that particles having greater than 1.2 will settle easily. The particles of specific gravity greater than 1.2 will settle easily. Then we have discussed enough about settling velocity. Then we have another velocity called as flow velocity. The another velocity is a flow velocity. What is this flow velocity? We'll go through here. The flow velocity is, let us consider this is a rectangle tank. Let us consider this is a rectangle tank. And in this rectangle tank, this is your length of the tank, and this is your breadth of the tank, and this is your depth of the tank. Right? Now the water will be allowed from here and the water will go from here. The water will go from here. Then flow velocity means how much water is flowing in this, with what velocity the water is flowing in this tank in horizontal direction, that is called as flow velocity. What is this flow velocity? Flow velocity, for that I have to complete this diagram, and then here I will be having some area. Right? This area I will consider. Let us know the Q value. Q value is known to us. How Q value is known to you? By population. You already know the population. You know already demand. You will multiply so many factors. Then after that, you will get a Q value. You know? Then this Q value is known. Then Q equal to A into V. Then V equal to Q divided by A. Then which area you are going to write? Here V is equal to Q divided by, this is a H and this is a B. Then if I write B into H, then this is your horizontal velocity. This is your horizontal velocity. Right? Now we can see here, this is your VH is horizontal velocity, Q divided by BH. Okay, now now we got horizontal velocity, and here some specifications are there. These you have to remember. That is, horizontal velocity must be 0.15 to 0.9 meter per minute. Normally for the design we will use it 0.3 meter per minute. Okay. When we go to the paper 2, SSC paper 2, when you qualify paper 1, we will discuss very detailed about this sedimentation tank and will solve many problems, because paper 2 is more about problematic. Then this is all about flow velocity. Now we will think of overflow rate. Overflow rate, or otherwise V naught, or surface loading. We will call it as surface loading. What is the meaning of surface loading? Surface loading, it is because here how much the water is moving, how the water is moving, because settling velocity is there. No, settling velocity is there means the water will be pulled downward by the specific gravity, then the water will be moving. Now I will consider this is called as the overflow rate. For that I have to take L and I have to take B. Then you already know Q is equal to A into V. Then V is equal to Q divided by A. What is this A? This A is B into L. This A is B into L. Now you will get this overflow rate as the Q divided by BL. Okay. Usually, actually, if you go through in detail about the sedimentation tank, this overflow rate don't have any meaning in a rectangular tank. Rectangular tank. It don't have any particular meaning in rectangular tank, but V naught overflow rate has a great meaning in a circular tank. In circular tank. How circular tank work? Here rectangular tank, I already told you that the water will enter from here, then the water will flow and water will come out. This is a rectangular tank. But how the circular tank will work? If this is a circular tank, then this tank will be of this design. Then the depth, then it will be made something narrow here. Then we will put one pipe here. This pipe will come here. This pipe is connected here. Then the water inflow will be from here. The water will enter from here. Water will enter from here. Then this water, entered water, is widened here, and this will be coming out here. Here small arrangement you can make. This water is coming out. Now you can see this is called as a overflow or surface loading. You are loading the water to the surface of the circular tank. Then this water is loaded. Then after that, this will move from here with some detention time. This will move to the periphery of the circular tank. The water will move in this direction. Then after that, this water will be coming out of this circular tank by periphery. This water will be coming out. Then you will make a small chamber here to collect that water. Okay, you will make a small chamber all along the periphery. You will make a small chamber all along the periphery, and somewhere you will make a collection point. Then the water will be coming out. This is a clean water. Right? This is a circular sedimentation tank where water enters here and comes here, and it will move along the periphery, and the collected water will come out. Here you will get a real meaning of surface overflow rate. Surface overflow rate. Now, then if this is the case, then where that settling velocity will be there? Settling velocity. If this is a particle, then this overflow rate will push this one out downward, and this particle will come downward. Or otherwise the water will be coming here and it will go. But here in this zone, you just concentrate. This blue color zone is there. No, here there is a one fight. There is a one fight that takes place in this particular zone. What is that fight is? The particles are moving up because the overflow rate is going in this direction, and the particles are having the some velocity here. They will come down. There is a some fight is there, that is the settling velocity and the overflow velocity. Considering all of them, we have to say that Vs should be greater than V naught. Vs should be greater than V naught. Then only we can remove the particles. Okay, sedimentation tank. This is the entire thing. Here is the pipe. Here is the pipe. This pipe will come here and water will be going and it will be out. Okay, here in the sedimentation tank, Vs should be greater than V naught. This we have to take care, and if it is taken care, then the efficiency is 100%. Very important question they will ask you in this exam is, what is the efficiency of the sedimentation tank? The efficiency of the sedimentation tank is only in two way I can explain. Either it is 0 or it is 100%. We don't have a efficiency of the tank something called 80% efficiency, 90% efficiency, 75% efficiency. No. Okay, we have either 0% efficiency or 100% efficiency. Therefore, if Vs is greater than V naught, that is 100% efficiency. Vs is greater than less than V naught, then that is 0% efficiency. First calculate Vs by using a Stokes equation, then you fix a V naught by considering this one. Here we have some relation, that is V naught must be equal to 0.8 times of Vs, so that Vs is less, V naught is less than Vs. Then for upflow clarifier, then you have equation. If you are using a rectangular tank, then use this equation. Then if you are using a circular tank, then use this as a area of the surface area. Then always remember this point, this neta efficiency is depending on Vs and V naught. Efficiency is depending on Vs and V naught. This is ultimate. For this one, very interesting and very good explanation is given in SK Garg. About 1 page or 2 page explanation is given to prove that the efficiency of the tank is not depending on the depth of the tank. Efficiency of the tank is not depending on the depth of the tank. That is proved here. Okay, in the SK Garg you can find it. Then you always remember this one. The above statement also valid for the horizontal flow tank also. Horizontal rectangular tank and circular rectangular tank, circular tank also it is valid. Now we have a flow, sorry, this page is repeated, just ignore. Then after that we have a horizontal settling tank, sedimentation tank, I already told. Okay. Till now, whatever I explained, I might be explained you the meaning of Vs, settling velocity, considering some diameter of the particles. I told you the principle of sedimentation tank where G is greater than 1 or 1.2, 1 or 1.2. This also I told. Then Vs should be greater than V naught also I told. No? Then I told you the efficiency is 100% or efficiency is if not meeting then it is 0%. This much I told you. Okay. If at all there is a tank like this is a sedimentation tank. In this tank, the particles are entering here. The particles are entering here. These particles have a diameter d. These particles have a diameter d. Right? Then this tank is designed for this diameter. The tank is designed for this diameter. Means what? What is the meaning of the tank is designed for this diameter? Means I have 100% confidence or I have 100% efficiency to remove those particles. Means here the tank is designed for this one means it is 100% that I will remove it. Then now call this one as a D1 particle. Then I can remove all D1 particles. All D1 can be removed. Okay, in this tank, now tell me if another particle of D2 diameter and D2 is greater than D1 diameter, can I remove this tank will remove this particle or not? Tell me the answer. This tank will remove this particle or not?
Yes, sir, it will remove, sir.
Of course, because the size is bigger, then specific gravity is bigger, therefore the weight of the particle is bigger. Next question is, I have another particle, the particle size is a D3 and
ಕ್ರಾಸ್
less
ಮಾಡಿ
than,
ಲೇಟ್ ಸೆಟ್ಲ್ ಆಗುತ್ತೆ ಸರ್
huh?
ಅದು ಸೈಜ್ ದೊಡ್ಡದಿರೋದ್ರಿಂದ ಸೆಟ್ಲಿಂಗ್ ಆಗುತ್ತೆ ಸರ್, ಅದು ಸೆಟಲ್
Yes,
ಆಗುತ್ತೆ.
settling ಜಾಸ್ತಿ ಆಗ್ತದೆ ಮತ್ತು ಫಾಸ್ಟ್ ಆಗ್ತದೆ. Compared to the
ಓಕೆ ಸರ್.
design diameter, it will fast. Okay, now I have
ಓಕೆ.
another diameter D3 which is less than D1. Whether this particle will be settled or not? This particle will settle or not?
ನೋ ಐ ಥಿಂಕ್ ಸರ್.
Yes, the answer, exact answer is no. The answer is no. Why? Because these particles are smaller in diameter and this tank is designed. What is the meaning of designing the tank? The meaning of designing the tank is length of the tank and depth of the tank. Okay, usually length and depth of the tank and width of the tank. Okay, width of the tank, it is not there in this figure, therefore I will not consider. Okay, means I have made a proportion here L and H for D1 particle. This L and H proportion is made for D1 particle. Therefore, the path of the D1, the longest path of the D1 will be, it will come like this, it will come like this and it will be settled here. Let us consider the longest path is this one. This particle will come and settle here, this will be removed. Okay, if the particles of greater diameter will be having the path this one, they will come and settle here, greater diameter. Then the particles of smaller diameter, the smaller diameter particles will go like this, If there is an opening here, then the particle will go here. This particle is not removed. From this, what scientist thinks here, look at here. If the water is entering from here, this is the pipe. I'll show you in the green color. The green color pipe is there now here. The green color pipe is the water is coming from here. The water is entered here. Then of course, these particles, the D3 particles are not removed. Then scientist says that instead of putting this pipe here, then I will make this much of opening, then will allow water to come from here. Means some smaller depth is given and some more depth is given in the entry point. Then what happens? Concentrate on the blue line. this line is there, no, this is a escaped particles. Then the same parallel line if I draw from here, same parallel lines here, same parallel line if I draw, then it will settle. Right? Means, as I told you that here d1 can be removed 100% and d2 can be removed 100%, d3 is a 0% removal. If you allow the water, if allow the water to some height, some different height, then you can remove d3 particles also, you can remove some d3 particles, right? Now the question comes here, how to get this d3 particles, na? May I count all the particle diameter and d3? No. Here that comes, you do sieve analysis and you make some this one graph, and after that you design your tank for some diameter d. Then after that you can ensure that this will be removed. There is a big procedure for that one. In that big procedure you will come to know the efficiency of the tank removing the particles smaller than the design particles. Efficiency of the tank removing the particle size smaller than the design particles. There you may get something different value. Hanga 80% efficiency, 70% efficiency, 85% to 15% to 50%. Like that you can have some different number. These numbers are for other particles, not to the designed particles. Right? Any doubt till now here? If you have any doubt, you can ask. That is nicely explained here. That is these graphs you can go through, that I already explained. That is Vs equal to V naught is a 100% efficiency. Then if Vs1 is less than V naught, then higher particles that will be removed. Then Vs2 is a V naught, then how that will be removed, that is all explained here. Okay. From this you just think of this equation. This equation is efficiency equal to Vs by V naught. This is for the particles which are less than the V naught are designed. The particle size is less than the design particle. Then you can have this one. And this is also you can remember, that is H equal to K times H. What is this K? K is nothing but efficiency. K is nothing but efficiency. Very interesting. Now look at here. I have a 4 meter of tank. Height of the tank is 4 meter. Then if I am allowing the water from 2 meter, then what is this one? The small h is what? Small h is 2 meter. Let us consider some different value, 1 meter and 3 meter. Okay. What is the small h? Small h is a 3 meter. What is the capital H? Capital H is a 4 meter. Then substitute here, h is equal to k into h. Then what is the small? Small is a 3. Then k into 4. Then what is the k equal to? 3 by 4. 3 by 4 means what? 75%. Now I can say that the efficiency of the sedimentation tank removing the smaller particles is a 75%. Very easy. All the theory whatever I explained, that will fit into this one. Right? Now for a plain sedimentation tank, these values you just by heart this one. For a plain sedimentation tank, overflow rate is 500 to 750 liter per hour per meter square. What is this per meter square, that we will see here. Let us consider this is your sedimentation tank of some length LB breadth. Then I will consider 1 meter here and 1 meter here. This is a per meter square. This a space. This space will remove. This space will have a velocity 500 to 750 liter per hour per meter square, per hour it is. Okay. Or you can say 12 to 18 meter cube per day per meter square. You just by heart this one. Okay. Na? Then after that we have a detention period. Detention period is the Q formula. You just have this equation, that is a dt equal to volume of the tank divided by rate of the flow, because q equal to meter cube per second. No, meter cube per second means volume, and this is a t. You bring this side and q the other side, then the dt equal to velocity by q. Then dt means what? Detention time. Volume means lbh, and circular volume is something different. You by heart this one, because we have a circular tank with some conical shape here. For that one, some portion is added here. Therefore dt equal to this equation. Then, very important, remember for plain sedimentation tank 4 to 8 hours. In this page, these constants you have to remember. Important constants which are given in the notes that just you have by. And very difficult and deep things, don't worry, because we are answering 1 mark question in paper 1. Then flow through period. Flow through period means some particles will escape. You know, some particles will escape. That is studied. It is the average actual average time taken by the water to pass through a sedimentation tank. Okay, it is always less than the detention period. Why? Because the short circuiting will happen. The particle has to come from here and it has to pass through this one, all the way it has to go through. That is your DT, detention time. But the some particles will not go down. They will go top here and they will escape. You know, this escaping time is considered as a flow through period. And here also displacement efficiency will be there because escape is there, no, therefore efficiency will come. Flow through period divided by detention time, this is also time and this is also time. Okay, then the plain sedimentation tank is normally in normal condition can have about 70% of efficiency. Which efficiency? This one, displacement efficiency will have 70%. Okay, this homework is given. If you have a time you can go through. That is the type of sedimentation tank in details and inlet and outlet arrangements, how it is there. This is actually for descriptive type of answers. Cleaning and sludge removal, how they will remove the settled particles. And tube settlers, like that we have some other settling, this one, and their design you can go through. And there is a one velocity, scoring velocity. If the particles are scored means those sediments will move with some velocity at the bottom. That is a scoring velocity. We can go through that. Do you have any doubt in sedimentation tank or anything is not understood? You can ask. Any doubts here?
Hello, sir.
Yeah.
So that settling velocity is not only depend on diameter, no?
Settling velocity is particle diameter. It is depending on particle diameter. Settling velocity.
Not only particle diameter. It
It,
also depends on specific gravity also, no?
yeah, it is also depending on specific gravity. That equation factors affecting settling velocity is given here. Okay, it is
Yes,
depending.
the then that D3, no, sir, that can be settled down, no, if the specific gravity is more.
Yeah, that your observation is correct because D3 is there na here where it is 1 minute.
That diagram.
In that other one, no?
Uh,
Here
here.
D3 can be settled down. You are considering that
Yes.
other factors, but other factors for a particular tank is constant. No? Say your velocity is Vs is equal to 1.8 uh, g minus 1 g divided by 18 g minus 1 d square by nu. For a particular tank, for a particular time, temperature is constant, therefore viscosity is constant. Then specific gravity of
Okay.
the most of the particles. For example, you take a sand particles of bigger particle or smaller particle or very smaller particle. All are sand only, no? Therefore, specific gravity is
Okay.
constant for particular sand. Then G is
Yes.
also constant.
Okay. G is constant.
G is constant. Plus, sand. If sand silt is mixed, then I can say that G is varying. Okay.
Uh, okay.
Any other doubts? Okay. If you don't have any doubts, we'll move to the next chapter. Or if you have anything, any concept not understood, you can ask. Okay. Now we'll go to the next chapter. The next chapter concentrates on the particles which are very, very smaller than the sediments which are considered here. As I said that D1 tank is designed for D1, D2 is the bigger diameter, D3 is a smaller diameter. Now sedimentation tank was concentrated on the particles D3 also. D3 also removed. But there are some particles which are D4, they are very, 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 very smaller than D2. even in fact D1. Okay, in fact I can say that D4 is not a particle, is a colloidal. Colloidal also particle, but colloidal means what? They have some charging effect on the surface. You know, they have some charges. As I said, the clay particles, in geotechnical engineering, while teaching geotechnical engineering, I said that the particles have a negatively charged, then they will attract the water. Not only water, they can attract any other things also. They can attract any other things also, like that. If such particles are there, those particles are charged, and how to remove those particles? Okay, is sedimentation will remove those particles? No, they will never remove those particles. Why? Because look at here. Okay, those particles cannot be removed. Why? Because this is a particle of charging. No, this is also charged particle, this is also charged particle, sorry, this is minus. All colloidal particles will have a same charge. This is also charged particle, this is also charged particle. Now this minus and this minus and this minus and this minus, they will repel each other. They always repel each other, therefore they never settle down. Just best example is your milk. In the milk, white particles are there. Those white particles will never settle down. They will settle down when you put a drop of lemon. When you put a drop of lemon, then they will attract each other, and after that they will settle down. Okay, na? That is called as spoiling of milk. Understood? Huh? Now, such particles, smaller particles, how to remove these smaller particles? For that, we have a chapter called as coagulation. Right? Coagulation or coagulation aided
Hmm.
sedimentation tank. Here, to remove very fine mud particles and colloidal particles, we are using this coagulation tank. These colloidal particles generally will not settle easily. Okay, to make them settle, their sizes are increased. Okay, their sizes are increased. This is one particle, this is another particle, this is another particle, another particle. They are repelling each other. I have to make some arrangement so that here some another layer is formed, and gelatinous layer we will call. Gelatinous means gum type of layer. Some gelatinous layer is formed, and this gelatinous layer will attract all the particles and make this particle big. When this particle is big, then it will have a weight. Then this weight will allow that to settle down. Okay, na? It is said, by bringing them together by means of gum like molecules called as flocks. They are called as flocks. These flocks attracts colloidal particles. They will attract the colloidal particles, and after that these bigger size particles will settle down easily. The process is called as coagulation. Okay, na? Then the chemicals used for this process are called as coagulants. The chemicals whatever you are adding now, that they are called as coagulants. Then the gelatinous precipitation which forms in the tank by adding coagulation is considered as a flux. Then most of the colloidal particles are negatively charged. Always remember, most of the colloidal particles are negatively charged. Just remember a clay particle. Clay is a smaller size, and you already know that in geotechnical the surface is negatively charged. You just remember the clay means it is a family of colloid. You can consider that is most of the colloidal particles are negatively charged. Coagulation. What is the meaning of coagulation? It is adding coagulation and mixing them. Both together it is called as a coagulation. Then coagulated water will further pass through sedimentation tank. Therefore, whenever you are providing a coagulation tank, then this is your screening. That water will go through coagulation tank, that water will go to sedimentation tank. If you don't have a sedimentation tank, then screening, and after that directly sedimentation tank. Understood? Then coagulation water will pass through sedimentation tank. Coagulation is generally necessary if the turbidity is greater than 30 to 50 mg per liter. Very important. Then only we will provide coagulation. Efficiency of the removal of flocculant suspension is determined by settling column analysis. There is one experiment called as settling column analysis. We don't have any mathematical equation for efficiency here in coagulation tank. Then chemicals used for coagulation. Till now we have a 4 type of chemicals we are using it as a coagulants: alum, copperas, chlorinated copperas, sodium aluminate. Right? Now we'll go one by one. Alum is a general name which is also called as aluminium sulfate. The formula you by heart this one: Al2SO4, Al2SO4, 18H2O, Al2SO4, 18H2O. You just by heart this one. Then see here, equation, this big equation is not required, but you should know this one. Alum is mixed with the calcium bicarbonate. You remember like this: alum mixed with calcium bicarbonate and produces calcium sulfate and flux. Always remember, this is your flux. This is your flux. Al is missing here. AlOH thrice. I think Al2OH thrice. We'll see another equation. Al it is. Okay. AlOH thrice is there, no? This is your flux. Okay. Means you just remember in this equation what is there. Okay. Concentrate, because they will definitely ask such easy questions. That is, alum is mixed with the calcium bicarbonate, produces calcium sulfate and one flux. This CO2 will go and this water will be in the water. Okay, means most important is four terms are there. Now look at here, what is this calcium bicarbonate? May I call this one as alkalinity? Yes, because HCO3 is there, therefore this is alkalinity. May I call this one as a hardness? Yes, this is also called as hardness. Which type of hardness it is? It is a temporary hardness, carbonate hardness. Right? This much is clear. Okay, means to add alum, water should be hard. To add alum, water should be hard. Okay, then when you add a water should be temporary hard. Then when you add a alum, then it will produce permanent hardness. See this one, you go through the previous lecture. Calcium sulfate is a permanent hardness. Right? This is a permanent hardness. Means permanent hardness is induced. Alum, if you add, then you will get a permanent hardness into it. Then one more demerit is CO2. You go through the chart given for acidity. Acidity is caused by 4 parameters I have given. In that CO2 is also there. Right? Means by adding alum, the acidity will increase. If the acidity is increased, what happens? Corrosion will be there in the pipes. Therefore, adding alum will introduce you corrosion. Adding alum will introduce you permanent hardness. These are the two demerits. Right? Next, these are all written here. Now look at here. Alum is working with what? Alum is working with the calcium bicarbonate. Calcium bicarbonate. Calcium bicarbonate, when it will be available in the water? See here, this is a carbonic acid, pH 0, pH 14. Then where is a 7? 7 is here. This is your 7. This is a pure water. This is alkaline, and this one is this is acid, and this is alkaline. Alkaline means what? It is CO3 or HCO3 or OH. Right? Now look at here. OH is means if the water has a OH, if water has a OH only, then its pH is from here to here. Okay, this scale is there. Now this scale you by heart this, not only for this chapter, it will be useful for other chapter also. If the water has only OH content, then the pH is from 10 to 14. 10 to 14. If the water has a pH of 8.3 to 10, then water will have alkalinity due to OH and CO3. Then if the water has a pH of 6.5 to 8.3, then it will have alkalinity due to these two compounds. Then if the water has a pH from 4.5 to 6.5, then it will have a only HCO3. Very important, only HCO3. Understood? Then if a water has a less than 4.5, then it will have a carbonic acid. Other acids also there, but we are discussing about calcium, no? calcium, calcium, calcium. Everywhere calcium is there. Therefore, carbonic acid will be there here. Understood? Now, from this diagram, where you are getting HCO3 in the water, you are getting HCO3 here and here. Okay. Therefore, average algae. Okay, that I will explain. Then your alum addition will be very effective when the pH is near to the 6.5. We'll answer it like this. If the water is near to the 6.5, then it will be very effective. Okay, the algae raises the pH in water above 8.5. You remember this one. Whenever you add algae to the water, then they will raise the water, they will raise the pH of the water. Okay, how much? 8.5. Then OH and HCO3 cannot be present at a time in water. Always remember this. Where is the OH, HO3 with blue color, concentrate on a blue color. See here, HCO3 is here and OH is here. Okay, they are very far away from each other. OH and HCO3 cannot be present at a time in a water. As pH starts falling below 8.3, all carbonate alkalinity starts converting into alkalinity due to HCO3. That is already shown in the scale. Coagulation process is made effective between 6.5 to 8.3. Very important. Okay, 6.5 to 8.3. Now you might be asking one question, sir, how come it is possible? Because only HCO3 is available in this scale, no, that is not true, because here CO3 is there and HCO3 is there. Interchanging is possible here, but here it is alone is there, no, therefore it will not mix with some other material. Here there is a mixing and dissolution is possible. Therefore 6.5 to 8.3 is a correct pH range for effective coagulation. The amount of alum to be added depends on the amount of turbidity in the water. We already discussed. Usually alum dosage is 5 mg per liter for clean water to 85 mg per liter for more turbid water. Usually in normal condition 17 mg per liter we will be preferring. Right? If alkalinity due to bicarbonate is not there, question. If the alkalinity due to bicarbonate is not there, means if a water don't have HCO3 alkalinity, then what? Then you prepare this one, then you produce this HCO3, or otherwise we have another equation. Okay, you prepare this one, you take a small container, you prepare this one alkalinity due to HCO3 minus, then after that you add that one to the water. One option. Otherwise our alum, our fellow alum is can this one react with calcium hydroxyl also. ये कौन है? This is a enemy of this HCO3. I already told you that OH and HCO3 both cannot be there in the same water, है ना? Because OH is there means HCO3 is not there, HCO3 is there means OH is not there. Okay, एक जंगल में दो शेर नहीं रह सकते साहब, ऐसे ना. The same way, if this lion is there, then our alum will react here. If it is not there, then it will react with this one. See here, CaOH twice is there. Then what will it produce? A flock? Yes, it is produced. Look at here, it is produced the flock. Will it produce this one permanent hardness? Yes, it is produced. Means merits and demerits are same. Merits and demerits are same. And will it produce CO2? No. Okay, if it is reacting like this, then the CO2 liberation will not be there. And another one is, we have another this one CO3. It can react with sodium carbonate also. It can react with sodium carbonate also. Okay, will it produce a flock? Yes, Al2OH thrice produced. Good. Then will it produce a permanent hardness? No. The permanent hardness is not produced when alum is mixed with sodium carbonate. Understood? Sodium carbonate. Therefore, this is a very interesting. No? If you have a sodium carbonate in the water or add sodium carbonate into the water, then alum will be working, flock will be generated, your purpose is met, and permanent hardness is not induced. But why we are not using this one? Because this is costly. This is costly compared to the above equations. Therefore, and adding of lime also reduces the taste and odor along with the turbidity. Important. Okay, na? This is
So,
alum.
so,
Hmm.
so this is why the ideal pH is 6.5 to 8.3 because CO3 is present uh, between 6.
Alum will react with even CO3 also, no? Therefore, 6.5 to
Yes.
8.3 is the correct answer. So that you will have CO3 also and you will have HCO3 also.
Sir, one more explanation what you gave 6.5 to 8.3.
Now, one more explanation is this HCO3 is there, no? This is only HCO3. Exactly, I don't know the reason this only HCO3 will react with the alum or not. But here conversion is there, no? That conversion will help us, our alum to react. Okay, because this HCO3 alone is there, no? This may be with other compounds, not only with the CaHCO3. Okay, if I have a CO3, then I can have a alkalinity and temporary hardness and the reaction. You know?
Yes.
That's why
Thank you.
4.5 to 8.5, even though only HCO3 is there, but it is not considered as effective. Okay. Now, considering all these points and this one calcium temporary hardness is very easily available in the water, and considering the pH of the water, then alum is a suitable or cheap material for alkalinity. Then we have another one. Second one is the copperas. The copperas, another name for copperas is a ferrous sulfate. Copperas is a ferrous sulfate. Then copperas always react with a hydrated lime. Copperas always react with the hydrated lime and forms of flocks. Here, remember, this is your flock. Okay, this is your flock. FeOH twice. Now, look at the reaction. This is our copperas, then reacting with hydrated lime. Then after that, it is also producing permanent hardness. Okay, of course, flock is generated. Permanent hardness, it is also producing. Correct? Then the second case, when copper is added earlier to the lime, here two things will come. Okay. Now a copper is added to lime. Okay. This one, this reaction will take place. Okay. Copperas is added to water, but water don't have a lime. Later you will add a lime to the water. Understood? This two reactions you have to remember. The first one is the first one is the water has a lime content or this one temporary hardness, or otherwise lime content is there, alkalinity is there, or you are adding lime to this one. Then after stirring this one, then you will add a copperas. Sometimes what happens, you will add a copperas first, then after that stirring this one, then you will add a lime. Two equations we will be getting. Then the first case will give this permanent hardness also, flock also. But when copperas added earlier to the lime, then this copperas will react with the present, that calcium bicarbonate present in the water, it will react with this one. But will it produce a flock? No. Yet the flock is not produced here. But permanent hardness is produced, flock is not produced. Here one more compound is there. This compound, for that compound to convert flock, I have to add a lime, hydrated lime. Then when I add a hydrated lime here, then it will produce a flock. Okay, the addition excess whatever you added, it will be precipitated. CO3, CaCO3 is precipitation, it will be settled down. It will be whatever the additional whatever you added, that will settle down. Okay, the copperas is used for raw water without colored, no, without colored, might be there. I'm confusing with this word colored, why it is there, not remembering. Okay, copperas is used in the raw water, that is for sure. It is effective in the water having pH greater than 8.5. Some textbook will give 8.3, some textbook will give 8.5. Don't worry, pH is greater than 8.3, this will be very active. Okay, then copperas is cheaper than the alum. Copperas is cheaper than the alum. Then okay, flock can be generated. This is also one equation is added to that. Understood? Now coming to, but still here you can discuss here. Copperas is cheaper than the alum, but still we are not using in place of alum. Why? Because the pH should be greater than 8.3. pH should be 8.3. Then chlorinated copperas. we have another one chlorinated copperas, but we will be not having that chlorinated copperas. First we will be having a copperas. For that one we have to add chlorine, then we will generate chlorinated copperas. The chlorinated copperas we will get it in a two form, that is and ferric sulfate and ferric chloride. Okay, we will get a two form. Then these two are called as a chlorinated copperas, and they will react like this. Okay, ferric sulfate and ferric chloride will react with calcium hydrated lime, and again they will produce a permanent hardness. They will also produce flux. Here these flux can be used, you know. Here when we will have these two equations, no? For that one it is written ferric sulfate and ferric chloride together is called as a chlorinated copperas. Also removes color, very important, also removes color. pH, ferric sulfate is effective in the pH range 4 to 7, and ferric chloride is effective in the range of 3.5 to 6.5. It's not like both will be reacted, no, it is all depending on the pH value. If the pH satisfies this one, then this fellow will react. If the pH satisfies this one, then this value will react. Then the question here is chlorinated copperas, the range of pH is what? For range of pH is 3.5 to 8.5. See, the pH range is this one. Therefore chlorinated copperas is something which has some good property, you know, it will react with a broad range of pH. By adding chlorinated copperas, permanent hardness induces, again it will induce. Then the last one is very interesting, and sodium aluminate, very interesting and very good coagulant. Look at here, sodium aluminate is there, which will react with what? Temporary hardness, and converts it in this way, and this way, and this way, and this way. Right? Here, this is a flock. This is a flock. Okay. Is it a permanent hardness? No, it is not permanent hardness. By adding sodium aluminate, you don't have any permanent hardness induced. Good, no? Then one more very important thing is, if any permanent hardness is there in the water, it will react with the permanent hardness, and it will not produce permanent hardness. See, sodium aluminate will react with the permanent hardness, and even it will see here, it will react with the permanent hardness, then it will produce a flock. It's very interesting, no? Therefore sodium aluminate is always good. This coagulant is 1.5 times costlier than the alum, you know, saukar. That's why it is giving some good results. This is used when water do not have natural alkalinity. Natural alkalinity is not there, then they will use. This coagulant reacts with both CH and NCH and removes both forms. Both will be removed, no? Therefore used for treating boiler feed waters. In boiler feed waters, the softening or otherwise that hardness will be should be very less. Therefore we will use that one. Water always tells like this one. In last class also I told you that sodium means what? Always remember this. Sodium is there means it will not make friendship with anyone. See here, sodium it has a very good friendship with the Cl, SO4, you know, such things. Therefore, but Cl and SO4, if that is with the Ca, permanent hardness. If this is with the Ca, this is permanent hardness. लेकिन सोडियम आ गया, तो सोडियम आ गया तो ये फ्रेंडशिप ब्रेक हो जाएगा, है ना? That friendship will be broken, and these will come with sodium. ಅಣ್ಣ ಬಂದ ಅಂತೇಳಿ ಅವು ಬಂದ್ಬಿಡ್ತಾವು ಸೋಡಿಯಂ ಬಂತಂದ್ರೆ. ಅದಕ್ಕೆ ಸೋಡಿಯಂ ಇತ್ತು ಅಂದ್ರೆ permanent hardness break ಆಗ್ತದೆ. That's why I have written here, water always tells like this. अगर मेरे पास सोडियम होता तो परमनेंट हार्डनेस का वाट लगा देता. ಅದರ್ವೈಸ್ ನಾನು ಬರೋ ತನಕ ಯಾವ್ದ ಹವಾ ನಾ ಬಂದ ಮೇಲೆ ನಂದೇ ಹವಾ ಅಂತಾರಲ್ಲ, ಅದನ್ನ ನೀವು ಸೋಡಿಯಂಗೆ ಯೂಸ್ ಮಾಡ್ಕೋಬಹುದು. ಓಕೆ, ನಾ ಬರೋ ತನಕ ಎಲ್ಲರದು ಹವಾ, ಪರ್ಮನೆಂಟ್ ಹಾರ್ಡ್ನೆಸ್, ಟೆಂಪ್ರರಿ ಹಾರ್ಡ್ನೆಸ್ ಎಲ್ಲವೂ ಇರ್ತಾವ ಒಳಗೆ. ಸೋಡಿಯಂ ಬಂದ್ಮೇಲೆ ನಂದೇ ಹವಾ ಅಂತಾರೆ. Okay, that you can remember. This chapter, all coagulants considered are reacted with the calcium in one or the other way, but all those reaction can also be written with magnesium. I have concentrated on calcium, but you can write all the equations with magnesium also. Okay, with some precautions. Right? Next important points are there here. Whatever we discussed here, those points you can go through. Right? Design of coagulation cum sedimentation tank. Here this is also something like a sedimentation tank only, no? Therefore design is not explained much here. Detention for this one is 2 to 4. What about plain sedimentation tank? 4 to 8 hours. More time taking in plain sedimentation, but less time is taking. Detention time for flock chamber 15 to 40 minutes is enough. VH for flock chamber 0.3 meter per second. Overflow rate is 1000 to 1250. What about there in plain sedimentation tank? 500 to 750. Okay, now depth of flow flock chamber is half of the uh, coagulation aided sedimentation tank. Okay, you can go through these homework. Constituents of the coagulation sedimentation tank: dry wet feeding, and these are all operations, and some troubles will be there with the coagulation that you can go through as a homework. Do you have any doubts in coagulation tank?
ಸರ್
Hmm.
ಸರ್ ಈಗ ಯಾವ್ದು ಕೋಆಗುಲೆಂಟ್ ಯೂಸ್ ಮಾಡ್ತಾರೆ ಸರ್
ಈಗ
ವಾಟರ್ ಟ್ರೀಟ್ಮೆಂಟ್ ಪ್ಲಾಂಟ್?
ಆಲಮ್ ಯೂಸ್ ಮಾಡ್ತಾರೆ.
ಓಕೆ ಸರ್.
ಆಲಮ್ ಯೂಸ್ ಮಾಡ್ತಾರ. ಸಾವುಕಾರ ಇರ್ತಾರಲ್ಲ, ಫಿಲ್ಟರ್ ಇದನ್ನ ಏನು ಸ್ವಿಮ್ಮಿಂಗ್ ಪೂಲ್ ಇಟ್ಟವರು, ಅಥವಾ ಮೆಡಿಕಲ್ಸ್ ಒಳಗಡೆ, ಅಥವಾ ಟೆಕ್ಸ್ಟೈಲ್ ಇಂಡಸ್ಟ್ರಿ ಒಳಗಡೆ, ಬಾಯ್ಲರ್ ಫೀಡ್ ವಾಟರ್ ಅಲ್ಲಿ ಅಂತಲ್ಲೆಲ್ಲ ಸೋಡಿಯಂ ಅಲ್ಯೂಮಿನೇಟ್ ಯೂಸ್ ಮಾಡ್ತಾರೆ.
ಓಕೆ ಸರ್.
ಅಂಡ್ ಒನ್ ಮೋರ್ ಥಿಂಗ್, ಅಲ್ಲಿ ಬರ್ದಿದ್ದೆ, ಐ ಥಿಂಕ್ ಐ ಡಿಡ್ ನಾಟ್ ಟೋಲ್ಡ್ ದಟ್ ಒನ್. This point here, iron salts are there, no? Iron salts produces more flux than the aluminium. Okay, these points will answer most of your questions. That Fe salts are more effective. No? More flux produce, that is the iron salts produce more flux. Why you want more flux? Then if you have more turbidity means what? Wastewater. Wastewater treatment. If you want to do wastewater treatment, then use iron salts. What is this iron salts? Copperas, or chlorinated copperas, or plain copperas, that you will use. Iron salts are very good oxidizing agent. Removes H2S, taste and odor. H2S ಅಂತಂದ್ರ it is very, this one very this one toxic ಅನ್ನೋದು ಏನದಕ್ಕೆ bad smell, that will be removed. Means what? Wastewater treatment. Iron salts are used in wide range of pH. That is already told. Iron salts causing straining and produces iron bacteria. This is very important. And this will be not used in drinking water. Why? Because iron salts will produce staining. If you are using iron salts and washing clothes, then white cloths will get some bad staining on that one. Then iron salts helps and imparts corrosiveness to water. Okay. Then to handle iron salts, skilled laborers are required. Very important. Then iron salts are more frequently used to treat the wastewater, considering all of them, and more uh, wastewater, and alum more frequently used for treating raw water. Any doubts? Okay, no doubt. Now we'll take a small break. Now it is 9:47. We'll come at 9:57. Right up? 10-minute break. Thank you. Welcome you all. Now the next chapter, filtration. Okay. Now we have concentrated on the big particles like trees, bushes, big stones and all. Then later we concentrated on small particles. Then after that we have concentrated on colloidal particles. Right? Then we will go still further smaller than that, or otherwise some other particles. Okay. It is to remove discrete or flocculated or bacteria present in the water, or color, odor, turbidity. These all will be removed in one that method, that is called as a filtration. Okay, na? Now in this filtration, the process of passing the water through the beds of granular material is known as filtration. Okay, na? The process of granular material will be there. so that the water is passed, that is a filtration. Now filtration classification based on the role of filtration, we have two types. The first one is slow sand filtration, rapid sand filtration. In rapid sand filtration we have two types, that is a rapid gravity filtration and pressure filtration. This is a filtration based on rate. Rate means what? This will be with a slow rate, then a high rate, then this is high rate, then more than this rate. Okay, that is the rate of filtration. Then we have another one, that flow of water in the filter. The first one is a gravity filters and the second one is a pressure filters. With the gravity the water will be flowing from one point to another point, that is slow sand filter and rapid sand filter, but the flow is based on the pressure. We will apply some external pressure to pass that water through. Okay, then how this filtration, what happens inside the filtration, you know? There are four mechanisms they will explain in the filtration. The first one is a mechanical straining, flocculation and sedimentation process, and biological metabolism, electrolytic changes. These four mechanisms will happen in the filtration. Okay, this is the theory, means why filtration and what happens, why these all will be removed, you know, those particles will be removed, that will be explained. Mechanical straining, here for example this is your filter body, and you have particles which are more than the your whites. Here whites are there, no? The particles more than the whites will be arrested. The particles which are the greater size than the whites will arrest between the whites. The most of the particles removed at upper sand layer. Okay, if this is the filter, then you have some layer here and layer here. In the upper sand layer only these particles will be arrested and that will be removed. Then coagulated flocks which are arrested also, which are arrested and also arrested smaller particles. This full stop also arrests smaller particles, means coagulated flocks in that the flocks which are coming from the coagulation tank, if anything are removed, if any flocks are removed, sorry, retained, those flocks will be removed in this filtration. This is called as mechanical staining. Then flocculation and sedimentation. Whites present in the sand media acts as a tiny coagulation cum sedimentation tank. What they say here is, if this is a void, this is the particles, sand particles, and here connectivity is there. Here water will this small void will act as a sedimentation tank and water will store here, and this water inside small particles will settle here, means flocculation and sedimentation both will be happening in the filtration. Okay, then biological metabolism, that certain microorganisms and bacteria are generally present in whites. Okay, there are some microorganisms like bacteria, non-pathogen, pathogens, they will be present in the whites. These organisms consumes organic impurities. If let us consider this is a one white here present inside the filtration, then here some bacteria are there and impurities coming there, that will eat those impurities, such as algae and planktons, etc., as their food. They will eat them as a food. Then they convert them as a harmless compounds by metabolism. Means they will eat it and they will consume it and they will produce outside that waste. That metabolism reaction will, that activity will happen, and they will produce harmless compounds. These harmless compounds so formed are layers. As a layers, the top is called as a scums, and the other is dirty skin. That is called as dirty skin. Okay, that can be removed. Then electrolytic changes, theory of ionization. Here theory of ionization, positive and negative, they will attract each other and that will be removed. It changes chemical characteristics of water. Sand in filter media and impurities carry opposite charges. They neutralize each other and make water pure. That's it. Okay, that electrical charges will be there. Now, which material we are using in this filter media? We are mainly using a sand as a one material, and we are using gravel as another material. Two important materials we are using. What are the specification of these materials is, the sand must be from, that is quartz and free from dirt. This is a common sense. Then the second one is in front in uniform in size, informal, uniform in size, that should be uniform in size and shape, means all particles must be of a same size, and that should be hard and resistant means it is also common sense. It shall not lose a weight of more than 5% of after soaking into HCl, means some hardness test they are doing here. Okay, for 24 hours. If those are that were soaked in HCl, then after that lose weight more than 5%. Then D10 is considered as effective size. In geotechnical, we know that in slow sand filter, the D10 value must be 0.2 to 0.4 mm. In rapid sand filter, 0.35 to 0.55 mm. Then CU, coefficient of uniformity, it should be 1.8 to 2.5, 1.3 to 1.7. It is coefficient of uniformity. Always remember, coefficient of uniformity is greater than 4 is a well-graded gravel. Well-graded gravel. Coefficient of uniformity greater than 6 is considered well-graded sand. But we don't want well-graded. We don't want well-graded. We want uniformly graded. Therefore, uniform coefficient is not matching this one. That is 1.8 and 2.5, 1.3 to 1.7. Okay. Next, gravel also we are using, that is a hard, durable, free from impurities, properly rounded gravels we are using. The density must be, dry density must be 1600 kg per meter cube, placed in 3 to 4 layers, each layer of 15 to 20 centimeter depth we have to maintain. Coarsest at the bottom and finest at the top. Coarsest at the bottom and finest at the top we are going to use. Now look at here, always in the filter media, the bottom material will be coarser material, top material will be smaller material. Why this is? Can anyone answer? Hmm?
Sir, to reduce the escape of finer materials.
Okay, to reduce the escape of finer materials. Okay, finer materials coming from the
Maybe so.
water will be reduced. Huh?
Um,
To reduce the velocity.
To reduce the velocity, that's also correct. Very important one. Two important points we
But
can
the
say.
So to
Hmm.
fill the voids.
To fill the voids, no, to fill the voids means these will come and fill in these voids, huh? No. Then it becomes well
The
graded.
top
Hmm? Hmm?
the top film formation will be easy.
Very good. The top film formation will be, that waste will be settled here, and removal is very important. That is very easy here. Okay, what happens if I put a coarse material here and a small material here, then the waste will come and settle here inside. Okay, I'll show in the other color. Let us consider green. This waste is coming, no? That waste will be settled here, 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 here. Everywhere that waste will be settled. Then how to wash this one? How to remove that waste? That is very difficult. And one thing. The second thing is that back washing will be very easy. If you are providing the that coarser material at the bottom, then the back washing will be very easy, because water will go very easily here and it will be retained here. Right? That is very good. Considering these points, we will be having smaller at the top and coarser at the bottom. Now, in India, it is not there. Anthrafilt, that one material is there. It look like a coal. It look like a coal. Then this is also used in some other countries, not in India, because it's not abundantly available in India. You can consider just for your information. Slow sand filter, slow sand filter and rapid sand filter. Two things are there. First, we'll discuss slow sand filter so that we can compare a rapid sand filter. Slow sand filter, you always remember, slow sand filter means old people, old aged people. They are very accurate and all, but they are very slow. You know? Rapid sand filter means youngsters. They are very fast, but they are not that much accurate. You know? Like that. Then and experience and removal, that everything we'll discuss like that. Can remove much larger percentage of impurities and bacteria. Okay, can larger percentage of impurities and bacteria, because experience. Slow sand filters yields very low rate. Very low rate. How much it is? 1/30th of rapid sand filter. If that 1/30th means, you just remember here, That is, if 30,000 liters that rapid sand is giving, then it will the slow sand will give how much? Cancel only 1,000, means 1/30th. That much slow it is. Okay. Usually coagulation sedimentation tank. Then after that the rapid sand filter. Then disinfection. Okay. Coagulation tank if you are using, then rapid sand you have to use. Then after that disinfection you will use. Therefore nowadays slow sand filter is not used. Okay, if you are using slow sand filter, then coagulation is you should not use. Okay, this is a point very important. Slow sand filter you are using means coagulation is not allowed. Coagulation aided sedimentation tank is allowed means slow sand is not allowed, right? That's why nowadays we are using coagulation aided sedimentation, therefore we are not using slow sand filter. Water enters into slow sand filter should not be treated by coagulants, that is, which forms a dirty skin that affects the working. Okay, that will form a dirty skin. Loss of head or filter head is limited to maximum of 0.7 to 1.2 meter. Means what? Loss of head, you always remember. See, this is your water tank, sorry, filtration tank, this is filter media. Then here you will put a water here, right? You will put a water. If I make a water to retain here, then after filtering the water, you'll tostini this side. The after filtering, if you put one piezometer, then the water will stand here only. It will not come to the original height. Then why this is? Because this is a loss. How much loss it will take place? 0.7 to 1.2 meter loss. Means this difference is then no the water level above the filter media and water level in the piezometer connected at the bottom. This difference is 0.7 to 1.2 meter. Cleaning is done once in month or thrice. Once in a month or three. Okay, cleaning is done very late. That's why it is very good, because lazy people can adopt this slow sand filter once or thrice, 3 months once you can come and clean it. Scrap to 3 centimeter top sand layer. There will be 3 centimeter, up to 3 centimeter that scrap can be there. 0.2 to 0.6% of total water filter is required for washing. Okay, how much is required? 0.2 to 0.6 means very small amount of water is required to clean the filtration. Manual labors are required. They are very important. You can consider merit or demerit. You can consider manual labors are required. Then 100 to 200 liter per hour per meter square rate. Very small rate it is. Only 100 liter it is giving in 1 hour for a particular meter square. 1 meter square it is giving. Therefore very slow sand it is. And highly efficient in removing bacteria. As I told, old age people, experienced people, therefore 98 to 99% bacteria will be removed. Then less efficient in removing color. Less efficient in removing color. This is your slow sand filter. Slow sand filter means
So
sand is not slow. Yeah, ask.
why less efficient in removing colors, sir?
Why less efficient? I did not collected that exact reason. Huh? No, I will not guess. I will give you answer later. No?
Okay, okay, sir.
Okay. I will note it down. I will give the answer later. Okay. Next, rapid gravity filter. Rapid gravity filter or rapid sand filter. Then forward working. Here we have two types of working in this RSF. One forward working and another one is backward working. Forward working means what? The water is coming from the top and it is filtered and the water is going out. Backward working means it is a washing of the filtration. Then value 1 is to allow water in and value. Okay, for this one we have to use one figure. Okay, I will show you that figure and later will come. This portion will consider later. Okay, I will show that figure because all numbers are there here, 1 2 3 4, that I will explain later. Next, we have some points here. Amount of water required for back washing is how much? 2 to 5% of total water filtered. The total water how much we filter, 2 to 5% will be used for back washing. Washing is done every 24 hours to 48 hours, means in one day or 2 day you have to start washing that one. Rate of washing is 15 to 19 centimeter per minute. Centimeter per minute. That is usually 45 centimeter per minute. That is all. For example, if your tank is of this much depth, it's of 2 meter depth, then the rate of washing, it will take this much of time, you can estimate. Approximately 15 minutes it will take. 15 minutes of washing it will take. Overall, to refunction the work, that filtration, because here the filtration is there, the forward working is also there, that you will stop this forward working, then after that backward working, that is cleaning will start. That cleaning and after that refunctioning will takes place in 30 minutes. Pressure at which back washing is done is 40 kilonewton per meter square. This much of pressure you have to apply and back washing you have to do. Then operational troubles we have here. Operational troubles made at last. This is covered later. Then rate of filtration, see here, 3000 to 6000 liter per hour per meter square. Very huge, right? Compared to that one. There we have observed 100 to 200 only. But here 3000 to 6000 liter per hour. We can, therefore, we can save some space. We can save space and that media. Media means that sand or gravel. That amount also you can save that one. Less efficient than this one, less efficient than this one, because 80 to 90% of the bacteria removal is there. That removes about 30 to 40 mg per liter of turbidity also. It will remove turbidity also. Helps in removal of color. Okay, this again I will give you correct explanation later. Next, we have a last one, pressure filter. The pressure filter nowadays we are using because we want more rate of filtration. Okay, like RSF only, this is like RSF only, means it is just like a rapid sand filter only, but the difference is it is in closed or airtight vessel, because you are applying pressure more than the atmospheric pressure you are applying, therefore you are making it closed or airtight, and through which water is to be treated is passed under a great pressure than atmospheric pressure. Okay, then pressure normally maintained between 30 to 70 centimeter of water. 32 meter of water. 30 to 70 meter of water means 300 to 700 kilonewton per meter square. In rapid sand filter we have only 40 kilonewton per meter square. Almost this is a, in backwashing we are using 40 kilonewton per meter square, right? But here how much it is? 30 to, where it is, that 300 to 700 kilonewton per meter square, that much pressure we are using. A rate is 2 to 5 times more than the rapid sand filter. Okay, can compare this pressure with atmospheric pressure. What is the atmospheric pressure in kilonewton per meter square? Anyone? What is the value of atmospheric pressure in kilonewton per meter square? No idea.
Uh, is it 0.103?
Mhm. See here, always you remember this hint. Okay, you consider 3-story building. No, 1 story, 3-story building. This is a 3-story building. Let us consider I have put one water pipe here. Water pipe here. Then you hold your thumb. You hold your thumb below this water pipe. Then this pipe is connected to syntax. A syntax of height. Height how much? 10.3. 3-story building approximately. 10.3 meter. Then whatever the pressure your thumb is getting now here, that is atmospheric pressure. Easy, no? Easy to remember. 10.3 meter of height. That is atmospheric pressure. Now look at here how to convert this one. Rho GH is your answer. Rho 1000 into G 9.81, I will consider 10. Then H is also 10. Then how much it is? 10 into 10 into 10. 10 into 10 is 100. 100, this 1000 I will write it as a K. Now it is Newton per meter square. How much it is? 100 kilonewton per meter square is your atmospheric pressure. But how much they are applying here? 300 to 700 kilonewton per meter square. That's why they said here, what they are saying here, they are saying that greater pressure than the atmospheric pressure. Greater pressure than the atmospheric pressure they are applying. Now look at here how much rate they are getting. They are getting 6,000 to 15,000 liter per hour per meter square. Very huge it is. Okay. Then high maintenance because closed is there, pressure you have to maintain, pressure is there means all pipes, nuts, joints, you have to take care so many things here. Then compared to rapid sand filter, less efficient to remove the bacteria. As the discharge increases, then the efficiency will be very less. That is understood. Then removes about 30 to 40 mg per liter of turbidity and helps in removal of color. Okay, that we'll see later. Do you have any doubts in this one? Sorry, one more topic is that I will cover. This one we have a Karman Cosne equation here. This equation we are using, or this theory we are using in backwashing. Okay, some this one values are required here. That head loss through the granular porous media, the head loss equation is given by this person. That is HF equal to FLV square VS square divided by GD 1 minus N by N cube. Here, this is something of altered equation of Darcy-Weisbach equation. Darcy-Weisbach equation is there. This is just altered that one. Okay. Then after that, what is this F here? That is a friction factor. Friction factor, he has given a big equation where Reynolds number is also there. In that Reynolds number, you can use this one, but Reynolds number is multiplied with some factor called as a phi. That is a particle shape factor. Okay. Then after that, usual formula. Then you will get F and then you will get head loss. Okay, head loss through granular porous media. Okay, not this one as a backwashing. This is a front washing only, but through granular media. Now, flow through expanded bed. Flow through expanded bed. That one Le divided by L 1 minus N divided by 1 minus Ne, where N is porosity. We are using porosity. Then Le is an extended bed. Say for example, this is our sand bed of L distance. And you want to extend this bed. Some other reasons you are extending this bed. Then you are putting some extra material that we will consider it as Le. Then here what they say is how much I have to increase this one, or otherwise what porosity I have to, what density I have to maintain here. For that they say that let us consider this is a Ne and let us consider this is N. If you know the porosity of the earlier bed, porosity of the recent bed what you are adding, then you can calculate how much you can add, or vice versa. If you have this one 1 meter and if you want to increase this one as a 0.2 meter, then you calculate any, then you will get how much compaction you have to do here. This is there. Then backwashing equation, it is very important. Very important backwashing equation. This is a Vs, that is a seepage velocity. Then you will use the backwashing velocity. You can calculate it by knowing some N value. Okay, now N is a porosity. Then head loss due to backwash. Very important is, let us consider you have a filter media here. This is the filter media is connected with some pipe here. Then your water is stored here somewhere. This is some backwashing arrangement is there. There your water is stored. Okay. How much height I have to maintain that water head in the tank? This is a H. If you maintain too much height, if you maintain too much height, then this water will come with high pressure and it will spoil this, erode this soil. This soil will be eroded. Therefore, you have to maintain very small height or particular critical height. In quicksand condition, you have used this one. Critical height you have to use, so that what happens, the boiling action will be taking place, and that boiling action will clean the sand surfaces. That will clean the sand surface and it will be removed. Okay, that's why here this equation used. If you are very familiar to equation, geotechnical equation, you can use this one. Say for example, N equal to E divided by 1 plus E. This equation is there, and you have equation IC equal to G plus 1 divided by 1 plus E. Sorry, G minus 1 divided by 1 plus E. What is this? IC is a H by L. Then look at here, H is equal to then L into G minus 1 divided by 1 plus E. Then what is this 1 plus E? This 1 plus E you take this side, then E is there, na? E is equal to N divided by 1 minus N will substitute. Then something alteration you have to do. L miss Midvi. G minus 1 is there as it is, G minus 1 is there. L is there as it is, L is there. 1 by 1 plus E.